Welcome back, my favorite OChem 1 class. I am so excited. It's been just a crazy semester, hasn't it? And we are nearing the end. In fact, we are only going to tackle one topic in this last unit. I'm so excited. We're only going to have a couple videos for this last unit, but it's one of my favorite topics. It's actually been around forever, and it's actually been a really big mystery. So I want to take this first video to kind of do some defining and a little bit of a journey throughout history, just in a very cursory way, just to understand the evolution of this idea that is called aromaticity. We're going to look at things that are called aromatic. And now in general, we would think of aromatic as, oh yeah, I saw this in Gen Chem. I would grab my yoga pants and light a smelly candle, find my Zen place, and I would find my balance in my reactions. Don't you love it? That's not this aromatic. This aromatic has to do with energy, not whether it smells good or not. So some of these might smell okay and some of them don't. So it's not just the smells. In fact, if you always want a nice sweet smelling something, you're going to go for the esters, not necessarily the aromatics. So let's kind of start with our journey. This is one big mystery for the last couple hundred years. In fact, this mystery was observed by Kekulé in the 1800s. So we're going to go about 1865. He published a crazy structure for something called benzene. And already scientists knew that benzene was a little bit of a mystery, but how to actually study it and unfold that mystery, that's what's going to evolve over the next 150 years of history. So what is benzene? Let me just draw you what we think of as benzene in that structure now. So it kind of looks like a cyclohexane, but you've got these alternating double bonds in there. That's why we save it for last. And Kekulé proposed a structure in 1865 and had some interesting ideas about the weirdness of benzene. But how do you actually study something like that? And one of those ways came in the later 1800s in a reaction that we learned that was hydrogen and palladium. Okay, so if you take hydrogen and palladium, we learned in our last unit that you can literally add a hydrogen across that pi bond or do a hydrogenation. So let's add one more piece of information to that. Shut the front door, do this reaction and stick a thermometer in it. Okay, well, not actually because it's a gas. So you're going to use something called bomb calorimetry to do that. But if you were to do that, let's go back to Gen Chem 2 and think about this for a second. What is the only thing you are changing in this reaction if you were able to do this reaction and stick a thermometer in it and use your specific heat, and what could you actually generate? Well, look at that. The only thing you're changing is that double bond. You're adding hydrogen to that double bond. So if you had a way to then gauge if this were exo or endothermic, you would learn the energy of that pi bond or that double bond. Wouldn't that be awesome? So that's where our little journey is going to start through our history of this idea of aromaticity. And we're going to learn from that. So I drew sort of a squished together crude energy diagram. But let's start our journey right here. Oh, that's a little chubby. Okay, hang on. Excuse me, Fluffy. All right, so we're going to start right here. So let's take and let's add hydrogen to our hexene. And let's go all the way down to our hexane. And it turns out that this process gives off 125 kilojoules. So that's right. That is a negative. That is exothermic. Okay, so that kind of gives us a gauge in our energy. That kind of tells us something about the energy and our stability. We can learn from that. So the more energy that you're giving off, maybe then the less stable that compound was. And then in general, what's super exciting is that let's say you give off that 125 kilojoules for one double bond. Well, as we go through history, we're starting to see more than one double bond. So let's try it again with 2 pi bonds, and let's do a little math, and let's guess that 2 of these is going to be about, somewhere around 250 range. Okay, well, you study, let's say, this one first, and sure enough, you're sort of close. You're pretty close to that. And then, son of a motherless goat, you tackle this one, and you think they should be the same. Both of them are a hexene or a hexadiene. They both have 2 double bonds. Well, why in the Sam heck are they different in their energy? So the first thing that we're discovering is, son of a motherless goat, it kind of depends where those double bonds are. These 2 are different only in one thing, and that is the placement of those double bonds. So our first concept is something called conjugation. Oh, my pen just... All right, so this substrate down here is in conjugation. That is alternating double bonds. And we're going to find in our whole aromatic system that this is rule number 1. So I'm going to scroll down a little bit and just start a list. And the first thing we've noticed is that conjugation actually does a little bit something wacky with the energy. In fact, you give off a little bit less energy, and these compounds then are just a little bit more stable. Just a little bit more stable. So when you have compounds that have conjugated double bonds versus not conjugated double bonds, they are different in energy. Conjugation leads to stability. Okay, it's going to give you just a little more stability. So those are just a little bit more stable. Okay, so then, just for funsies, let's go ahead and add 3 double bonds in there, and we should get somewhere around 3 times the energy. But take a look at this. This system is in conjugation, so we don't quite get that, what would that be, 375. We get actually less than that, because we've got that conjugation. So you can see right away that the placement of those double bonds is a big thing. So that's one of the first things they learned with their studies of hydrogenation is, okay, well, it actually depends where your alkenes are. If they're in conjugation, you've got different energy. And there's some explanations to that, and we'll get to that in just a second. And then, what's fun in organic chemistry is once you think you've got something tackled, you put a ring in it and you try it again. So let's just compare then with our cyclohexene. And let's do the same thing. We had just a little bit less energy when we did that hydrogenation and went all the way down to cyclohexane. This time we were exothermic by 118 kilojoules. Okay, that's not bad. That's respectable. And then again, if we add 2 of our alkenes in there and we have a cyclohexadiene, we saw that same phenomena. It matters where they are. Okay, we have a difference here in energy. Our conjugated was a little bit lower here on our energy diagram and just a little bit more stable. So there's our conjugation again. And then for funsies, let's go ahead and add 3. Okay, so now, you guys are getting the hang of this. You go ahead and throughout history, they started with those straight chain alkenes and then switched to these ring alkenes. And they thought, God bless it, I've got this nailed. I'm going to guess in theory, I already know about 120 for that first double bond. So in theory, I'm going to be somewhere around 360, although we did learn conjugation. So I'm going to guess just a little bit less because of this conjugation. All right, well, here's where the plot thickens. This is where the mystery gets huge. Son of a motherless goat. You run this reaction, and now we're in the early 1900s, the late 1800s, early 1900s. You feel like you're on a roll. You run this reaction, and holy crap, not only does this reaction not work, it really doesn't work. So you can't even complete your study in this way, because if you treat this with hydrogen and palladium, son of a gun, you get no reaction. And in fact, that's what Kekulé first observed. He observed the reaction of bromine with alkenes. Now, that's something we did in the last unit. And so naturally, throwing some benzene in there, you would think, I've got 3 double bonds. I'm going to have bromine everywhere. Hello, carcinogen. Let's do this. And what he noticed was he couldn't get it to react at all, and really felt like, wait, I mean, more alkenes, more better. This should really react, and it didn't. So this is really part of our mystery. This is theoretically what should happen, but not at all what's observed. In fact, we have to switch our catalyst, and we'll see this in our last video, or second to the last video, when we start doing reactions. We can eventually add hydrogen, but you have to change your catalyst. So it wasn't until in the early 1900s when they can actually get this reaction to happen, and they had to open up a whole sledgehammer on this thing and actually get this to reduce to cyclohexane. So that was the first observation, is our aromatics, our benzenes, specifically our benzene, right away we need to follow different rules. They are not going to react with the reagents we've learned all semester. We'll have a little bit of overlap, but it's going to be pretty small. And that's why we save this till the end. We're going to see completely different reaction conditions for our benzene. Our normal reactions really don't always touch that benzene ring. And then the second thing they observed, has anybody checked out this energy yet? Good Lord, that is not at all what you think. In fact, when you look at it in our energy diagram, holy crap, it is way down here. That deserves a sparkle pen. That entire benzene, by the time you can actually get this reaction to work and add hydrogen and platinum and add hydrogen across that benzene, you actually only release 208 kilojoules. So that is telling you that there is something that is quite stable in that benzene. Now, it can't just be the 3 double bonds. Whoa, we just made a connection here. Here's our 3 pi bonds. It can't just be that, because don't we have that right up here? Yes, and look at how different that energy is. So now what's the one thing that's different between this hexatriene and this, in theory, cyclohexatriene? The fact that it's in a ring. So let's scroll down to our list. Number 1, conjugation. Number 2, in a ring. All right, we have something going on in these systems and in the fact that that's in a ring. So our aromatics need to be in a ring. And as we work through the evolution of this process, we're going to notice something here in our ring. The theory is that those electrons don't have to share, let's color code, between only 2 atoms. Okay? And so, all right, let's think about this for a second. If these electrons don't have to share just between those 2 carbons, they can literally share through that entire ring system. So all 6 of those rings, in the old days, our benzenes were drawn like that. In the newer days, let's go back to Gen Chem 1 for a second. We are about to draw resonance structures. This is what resonance means. It means that those 6 electrons are literally shared over those 6 carbons in that entire ring. And when that process happens, these electrons are called delocalized. Let's get all physics for a second. Let's write out our fact that this is in resonance. Let's write out our physics for a second. You have a charge over a distance. That's what a bond is. Your electrons are on a fixed sort of scale. They're of distance. You just took your electrons and you just lengthened that distance. You are no longer between two atoms, you're between six. So that was the theory then at the time. That's still holding true. We're just going to add to it that our benzenes have this really special situation where these electrons can literally share over all six of those carbons, almost like a donut or a racetrack. That's the way I like to think of it. Those electrons are all sharing around that whole ring system. So our aromatics have to be in conjugation, or they can't be in resonance that way. They can't share. They have to alternate. They have to be in a ring so that they can share over a greater distance. And then number 3, that ring has to be planar. In order for those orbitals to overlap, for those electrons to all share over multiple carbons, they have to be planar. So our first 3 criteria, and there's only 4 criteria, don't panic. Our first 3 criteria are conjugation, ring, and planar. Okay, so we literally are going to picture those as like little racetracks for electrons. Your electrons are sharing over all 6 of those. Thus, the drastic difference in the energy, the greater stability of those compounds, and the drastically different reactivity. If your electrons are sharing over all 6 of those carbons, they're not anywhere near as reactive as our other just simple alkenes that we saw in our last unit. And we'll observe this in our reactions. You have to give them a major kick in the pants to get them to react. But this chemistry has also been around forever, so there are reactions with our benzene. So let's travel just a little bit through history. And this idea of aromaticity has obviously, like I said, been around for 150 plus years. So I just have a million links in this document for you. All right, I've got a nice kind of set of conjugation links for you if you want to check that out by MCAT takers. You may need to come back and get a little deeper with your conjugation. Conjugation we also see in our UV vis. So this is a functional group that we can see in organic too. When you've got lots of repetitive conjugation, this is where we see color. So carrots, tomatoes, lycopenes, chlorophylls, xanthils, all of those highly colored substances, you go look at their structures and you're going to find high conjugation. All right, then this concept of aromaticity, I wanted to give you just a million links for that. This one is super fun if you can get on to that Science Direct. So far we've got a list of 3 criteria. Things that are aromatic are conjugated. They are in a ring. And they are planar. So as of the 1800s, really the focus was on things like benzene. But then as we expand this idea, I wonder if other things can be aromatic. Now we're getting into about the 1930s. And now we've got a scientist named Huckel that is looking at other types of substances. So if benzene is aromatic, let's try some other rings. So classic, something like butadiene. Okay, doesn't that fit our criteria? It is conjugated, it is in a ring, and it is planar, except when you try to make it, that little sucker is going to blow up. I mean, it is almost the opposite of being aromatic. So in the 1930s, another theory came out that something like benzene is highly stable and it is aromatic. And then expanding this idea, well, son of a motherless goat, butadiene is the opposite. So starting in 1931, there's the concept of anti-aromatic. Okay, well, crap. How do we figure that out? So they started looking at all kinds of different ring sizes and different structures. What about a benzene that has, it's not even a benzene, but let's go up in ring size. Let's go up to this one. This one, anti. Well, let's go a little bit sassier and let's go even higher. And let's go to something like, I just gave it away for free. I'm not ready for that yet. Let's go with something that might have a little bit different structure and, oh no, my battery's low. And now you're back to aromatic. So in 1931, number 4 in our criteria emerged, and that is called Huckel's rule. And what he noticed, and we're going to spend a little bit of time on this as long as my pen doesn't die. What he noticed was that it actually depends on your electron count. All right, so let me just show you that I've got an absolute million links for the next 2 concepts of anti-aromaticity and heterocycles. Hetero means now we're going to throw in nitrogen, oxygen, carbon, and now we're evolving to modern aromaticity. Okay, it started with just benzenes and now it's grown to other ring sizes, so other rings. And now we're going to grow here to other atoms. All right, let's combine this and let's define that Huckel's rule. So let's start with the difference between our cyclobutadiene and our benzene. All right, if we look at how many electrons are in our racetrack, oh, that's not very visual, is it? Hang on, I can't handle that. That's gonna have to look like this. Let's color code. How many electrons are sharing in that racetrack? 4. How many electrons are sharing in this racetrack? Can I count? 6. How many are sharing in this racetrack? 8. All right, remember this is all nice and polar, and we are sharing in pairs of electrons. We're not talking radicals here. These are all pairs. So this is what Huckel's rule defines. These 2 are anti, and this is aromatic. So as you work your way through the ring sizes, what he noticed was alternating even numbers. Holy crap, let's say that again. Alternating even numbers gave aromatics. Okay, alternating, the other set of alternating even numbers gave us the anti-aromatics. Okay, so he put that in terms of math, and it's called Huckel's rule, and that is 4n plus 2. Now, the common misconception is that that means electrons. It does not. That just means an integer. So, in other words, let's start with 0, and what do we get? 2. If we put a 1 in there, we get a 6, and so on. And look, that's what follows your aromatics. So that is what Huckel's rule does. It just spells out this process. So if you start with the aromatics with 2 and you just alternate your even numbers, you're going to figure out your aromatics and your anti-aromatics. And then as we get bigger, it gets just a little bit more complicated, and then we're done with this idea. Let's throw in our heteroatoms. So now if you can figure out if you have conjugation, so let's take one of my favorites. Let's take this, okay? All right, so number 1, is it conjugated? Well, it depends what you do with your lone pair. So starting after, looking at Huckel's role and looking at all kinds of substances in the early 1900s, and honestly still today. So aromatics are everywhere. We're looking at them for all kinds of things in nature. My honors class right now in OChem 2, we're looking at large aromatic systems because they interact with light in a really specific way, and we want that in solar panels. So my OChem 2 honors class, we're making big aromatic structures on purpose. We want to see what those electrons are doing. So you can have either pi bonds or lone pair, either one, in conjugation, in our ring, and planar. And we have to have the right count. So we've got to alternate our count, etc. Okay, so if we can meet this 4, we actually have an aromatic substance. So something like this with our nitrogen, how do you know how to count it? This has to be planar, and it has to be within the ring. Okay, now if we were in class, I would make all of you model this sucker, but we're not, so I'm going to try and draw this somewhat to its side. And remember first, where are alkenes? They are perpendicular to that double bond, right? Okay, so it's kind of easy to see that these can sort of flow in a racetrack. They're all right there. Now it depends on the placement of your lone pair. My MCAT takers, this is a classic question to mess with you. All right, this nitrogen is tetrahedral. Where are your lone pair? They will default to the best energy. So if we look at a tetrahedral bond there, and we look at those angles of these orbitals, this is our 109. So if you were modeling this, you would notice that you could have your bond to hydrogen out here, and then that lone pair would be up there. And sure enough, you can connect all right there in a ring. So you do count these. That is 6 electrons, and this is aromatic. Now let me show you an example where you don't count the lone pair. Let's take something like pyridine. Okay, let's take the nitrogen version of benzene. Okay, now this one's really critical because if you count them in the ring, done, these are in the ring, that's 6 electrons. That's aromatic. But now if you have these and they count, now you have 8 electrons, and that's anti-aromatic. So how do you know? Again, you got to build it, and you've got to hit your 4 criteria. So let's build this, and let's look at where those lone pair would be. All right, look at the hybridization on this nitrogen. You can tell all of these are perpendicular. They're all in that racetrack here. They're all right there. You could tell that they would totally share like that. Where is this lone pair? All right, what is our hybridization there? Oh, it is not tetrahedral. It is sp2. sp2 is trigonal planar. You build the model set on that, and you're going to notice that they're sticking out here. They are nowhere near that whole ring of sharing electrons. They do not count. So I think the 2 tricky things about aromatics is remembering how to apply your Huckel rule, and number 2, you may have to actually look at your lone pair and figure out if they're in your planar system or not. Let's do another one. Let's do 2 more. Let's take an oxygen this time. Well, son of a motherless goat, you've got 2 lone pair. Okay, let's draw it to the side. Again, it's got to be in your ring. So these we can already tell are in that ring. But now let's draw our sp3 here. This is sp3. So that means you're going to have something here and something here. So the lone pair that are here, those are all going to share. Your lone pair out here, nope, wrong angle. So this we would count as 6, and that is aromatic. And we do not count those. Okay, I love it. Now let's look at something that's in everything from LSD to tryptophan. Let's look at one of my favorite aromatics, and that is our indole. Okay, let's look at it. Obviously, we've got a nice little benzene here. Okay, I love it. And then now that's 6 electrons. But now what do we do with the second ring? It's still flat. And if we count our lone pair, and that's 8 electrons, then it's anti-aromatic, but we've got another double bond there. That brings us up to 10 electrons. So if we draw that one to the side, we're going to notice that that is right up there in line with that ring, and our hydrogen is sticking out kittywampus. It's going to look like this. This would be your hydrogen. This would be that lone pair. So we absolutely have an aromatic system for all 10 of those electrons. So really, we're just coming back to a model set if you need one. And what you're looking for are your 4 criteria. Do you have conjugated, double bonds, or lone pair? Are you in a ring? Is it planar? And then your Huckel rule. Are you in the right number of electrons that are sharing in that whole system? And then we notice a drastic difference in energy in those, so their reactions are completely different. And then our next 2 videos, what we're going to do is turn around and take these benzenes and use them. I'm going to show you resonance structures, and I'm going to show you how to do synthesis with benzenes. Because their energy is so funky, they're actually used everywhere. They are in everything from plastics to your amino acids because of their stability, but they also need completely different set of reaction conditions. So let's pause this one. Let's stop for a second here, and let's take a look at, in our next 2 videos, we'll start to react our benzenes.